All right, welcome everyone, both to Chicago Water Week, Day 2, and to the Third Coast Water Seminar Series, actually celebrating 1 year today of Third Coast monthly seminars on various water topics. Really excited to welcome you all here to join us today. My name is Elena Harkness. I'm the Executive Director here at Current. And on behalf of all of the Third Coast partners, Northwestern University, the Argonne National Laboratory, University of Illinois at Chicago, University of Chicago, and the University of Illinois Urbana-Champaign, I am really pleased to welcome you here to this very important seminar on a critical topic, removing forever chemicals from water using corn-derived polymers. So we're going to get right into the heart of it in a moment, but I just want to, of course, put in a plug for Chicago Water Week and all of the great programming that has already happened and is still to come this week. So take a look at the QR code on screen, scan it, join us. Many of these events are open to the public and free, and lots of them are online. So we hope you will take a look and dive into one of the many different water topics that are on the agenda for the rest of the Chicago Water Week. If this is your first Third Coast Water Seminar Series, so glad you've made it today. And I'll just run down a couple very quick logistics items. We try to run this as an open Q&A session as much as we can. So we are very focused on one substantial speaker from the water research community. And so we'll hear from our speaker on that topic, but you can always submit your questions in either the chat or the Q&A, and I'll be moderating those as we go. And this event is being recorded. So the recording link will be shared on Current's event page and our YouTube channel after the event. You can also go back, rewind, and see all of the other earlier Third Coast Water seminars. Again, agenda is really simple. We'll be hearing from Dr. Will Dichtel today, who's the Robert Letzinger Professor of Chemistry at Northwestern University. And then we'll have our Q&A and get you out of here right at the top of the hour. Just a few opening words about Current and why we are here today. Current's Chicago's Water Innovation Hub. We're 5 years old, and we collaborate to grow an inclusive blue economy, help accelerate innovation, and solve persistent water challenges. Why are we here? Well, we are here in collaboration with all these powerful research universities and national labs because we all know we need more healthy water to drink, less flood water in our basements, more blue jobs, putting Chicagoans to work right here in our region, and also homegrown companies solving water around the world. And really excited today that our speaker is not only a researcher, but an entrepreneur himself. So we'll be hearing a bit more about that story, I'm sure. Current exists because we believe that people are not rallying fast enough behind the kinds of new ideas and technologies that are really going to drive solutions that we desperately need to solve water challenges, both here in Chicago and around the world. We know that innovation is challenging. We're here today with all of these different research partners and collaborators because water challenges often require interdisciplinary approaches to solve. So Current exists to build partnerships among the research community, as we have on display today, but also among industry and among government and nonprofits and individuals that are trying to figure out how to take more rational risks to try new solutions out. Current does that by trying to stay on top of the latest technologies and the best solutions. We know that the field is rapidly changing, awareness about water problems is rapidly changing, and we try to be an independent assessor and matchmaker to try to bring those best solutions to bear on the end users, like our utilities and industry partners, who can try them out and then help bring them to scale. But we're also more than a connector. So Current actually exists to bring new technologies and ideas into the marketplace and into the real world. So here on screen, you see one of our wonderful interns doing water quality sampling from H2 Now Chicago, our real-time water quality monitoring effort in the Chicago River. We just launched this Labor Day. If you've not already checked it out, h2nowchicago.org is where you can, and see on days like today how this really intense rainfall is affecting the river water quality across 3 different branches. So really exciting project and a representation of how we bring research partners together with technologists to try and test new technology with public sector partners to provide solutions that are useful to the public. And we also are always looking ahead to the frontier of what kinds of technologies can solve future challenges. We've got pilots in place right now with partners, including the Discovery Partners Institute, on sewage surveillance using wastewater as an early warning indicator for SARS-CoV-2 outbreaks. We're working on thermal energy recovery and understanding what the best solutions are out there in the world to recover heat from wastewater to use as a renewable energy source, which is a critical piece of the path to achieving our state's ambitious decarbonization goals. And finally, this is the segue to our speaker today, PFAS elimination, finding better ways to target and destroy persistent forever chemicals that are challenging our water systems everywhere. And while all hot water topics feel pretty hot to me these days, perhaps none so much as this forever chemicals topic. These are industrial products whose destructive lives far outlast their productive ones. And as we're learning every day more and more, they can cause myriad harm to humans and to our environment. So today's speaker has really built his career helping us to understand many dimensions of this problem and developing novel solutions to address it. As I said, he's both a researcher and an entrepreneur, and we're really fortunate to have him here in Chicago. So a really brief bio about our speaker. Will Dichtel is the Robert Letzinger Professor of Chemistry at Northwestern University. Oops, sorry about that. Bio on the wrong page here. Sorry, Will's research focuses on inventing new materials and new ways to make materials with the ability to contribute to sustainability. His recent projects have included the development of polymers derived from renewable resources that remove trace industrial chemicals from water and new methods to recycle plastics, previously thought to be unrecyclable, a very important contribution. Professor Dichtel has received his degrees in chemistry from MIT and UC Berkeley and did postdoctoral research at both UCLA and Caltech. In 2008, he began his research lab at Cornell and moved to Northwestern in 2016. His research has been recognized by many national and international awards, including a MacArthur Fellowship in 2015 and a 2020 Bolobnik National Laureate in Chemistry. So with no further ado, I'm going to turn it over to Will, our distinguished speaker today, and look forward to the presentation. Thanks, Will, over to you.
Thank you so much, Elena, for the very kind introduction and for all the work that Current does to promote water technologies, especially in the Chicago area. I'm really pleased to be here and to have the opportunity to share some of our discoveries and a little bit about the translation of those discoveries into the real world. So as Elena said, I'm a researcher primarily at Northwestern and studying the chemistry and of how to make new materials. Today we're going to focus on water, of course, and particularly on PFAS compounds. But I want to take just a very brief step back and give you some context on emerging organic pollutants in general, because PFAS are not the only class, but they are a particularly nasty one, given their environmental persistence. But these come from really our everyday lives and the industrial processes that support our everyday lives. So there's no getting around the fact that humans are going to pollute water to some degree, and we certainly can regulate things better. We certainly can do this better, but to at least some extent, we're not going to totally get away from this problem from regulation. So even as we advocate for much better stewardship of our resources, there's going to be water purification problems that are important. So humans put pharmaceutical agents, pesticides, industrial chemicals, household products, components of personal care products, they all go down the drain, or they all find their way into water resources. And that gives us really very large lists of chemicals that we can find in various waters, particularly as we start looking for them. So this is a study done by my collaborator, Damian Helbling, who's helped us a lot in understanding our removal technologies. He also just goes and looks for organic pollutants in various water resources. So this is just the Hudson River estuary. He went and found trace amounts of all of the chemicals listed on this slide. It's an alphabet soup of things to find. There are all sorts of compounds, things that are very common among lots of water resources, things that are sunscreens and pesticides and things of that sort, agrochemicals, industrial chemicals, things that we know to be to have negative environmental impact, things that we either know or suspect cause cancer or have toxicity at relatively low concentrations, including among them PFOA, which is going to feature prominently later. And then moreover, this is a mixture of hundreds or thousands of substances, and we don't really understand what we're doing here by putting all these things into the environment. And then ultimately, as they pass through our agricultural systems or our drinking water systems or just the environmental consequences of all of these substances potentially having either synergistic or antagonistic effects. These are all frontier questions. And so certainly we want to be able to remove PFAS and many of these other compounds from water selectively, particularly for drinking water, but also, as I'll mention briefly later, for wastewater. And so there are many complementary ways to do this. So this is kind of the 10,000-foot view as to how you can purify water from these emerging organic contaminants. There are processes like advanced oxidation. So you tend to treat water with a very reactive substance like ozone or UV light and strong oxidants. These have varying degrees of effectiveness depending on exactly what is targeted. One of the troublesome aspects of those kinds of technologies is that the byproducts of these degradation reactions aren't necessarily well understood or automatically benign, and so you can solve one problem but perhaps create others. There are other kinds of filtration solutions, such as reverse osmosis. That's commonly used for desalination, but it can also be used to remove organic pollutants. These are expensive and energy intensive, and so they also have their place, but not a final solution on their own. And then the mechanism that we're going to talk about today is absorption, and this is dominated especially right now by activated carbons. So essentially charred plant matter or those derived from coal. They're very high surface area materials that organic molecules tend to stick to a lot. And so these tend to be pretty good for a lot of these pollutants, but generally not excellent for automatically for every single one. Moderate costs for implementing these, depending on exactly the context. And one of the Achilles heels here is that almost everything sticks to them, including a lot of naturally occurring organics that can stick to activated carbon and dramatically reduce its lifetime. Okay, and so in our group, we were looking for solutions that might be a little bit more specific than activated carbon and also maintain desirable aspects such as being renewable. And what caught our attention is this sugar that is well known in chemistry. It's called beta cyclodextrin. And so it's kind of drawn here on the right-hand side of the slide with, kind of as a blue cup superimposed on a chemical structure there. And that blue cup really gives you an idea, a really good mental picture of the shape of that molecule. And so beta cyclodextrin, it's industrially produced directly from cornstarch. So it's nice and renewable. It's rather inexpensive. And it's already used in products that you may be familiar with, notably in Febreze for controlling the bad odors in various contexts. And the way Febreze works is largely how these cyclodextrins are going to work for us in water as well. So I've drawn the molecule PFOA here. What is special about cyclodextrin and this cup-like shape of it is that the inside of the cup is kind of greasy, and the outside of the cup it really likes to be in water. These OH groups interact with H2O quite well. And so it's kind of this little tiny nano environment that is a great binding site for molecules that have kind of a water hating component, such as the fluoroalkyl part of these forever chemicals like PFOA. They're characterized by having these portions where they just dock right into the cup, and they fit nearly perfectly down at the molecular level, so they can be very nice and specific and avoid fouling by natural organic matter. And so this is known and even quantified where we can define kind of the math of how well this process works. And so if you think about this as a reversible process, it favors the right-hand side under particular conditions by a factor of about 10 to the fifth. So very, very good binding site for a molecule like PFOA. And so the idea here is that, okay, we'd love to take these cyclodextrin cups, so, coming from corn and really, really good way to catch PFOA. And the only problem is that you can't just use cyclodextrin itself, because cyclodextrin is soluble in water. And so what we need to do with cyclodextrin is we need to link it into and convert it into a material that is insoluble in water, such that we can flow contaminated water over it or through it and have the cups catch all of the pollutants that we want to remove. And so the way we do this more technically is to take cyclodextrin and we take another molecule called a crosslinker. So that's shown here in red on this slide. It's this specific cross-linker is called tetrafluoroterethalonitrile, which is kind of hard to say, so we'll just call it TFN. And these, under particular conditions that are meaningful to an organic chemist, will start forming bonds between some of the oxygens of the sugar and the TFN. And that will happen multiple times until finally you can build up this whole kind of gnarled up network where we've linked all of our cyclodextrins into kind of an infinite structure. And so if you shrank yourself down and could see this down at the molecular level, it might look something like this, where we've got all of these different cups. They're linked by these TFN crosslinkers. And then by virtue of the whole system being kind of rigid, we got some rigid cups, and then the TFN itself is kind of rigid. These things can't really fill space perfectly well. They kind of get restricted, and so you enforce having some voids in this network, and that permanent porosity gives rise to the material having a high surface area, and it actually allows the pollutants to be able to reach each cup quickly. And so that's a key part of the design as well. And that's really what made this material special over other attempts to make polymers that contain cyclodextrin for water purification. Okay, so that was really the breakthrough that we made a few years ago that we've been really studying and improving ever since. So we had this first material. I still remember the day that we discovered this, and Aladin Alsbai, who's the lead author on this paper, came in and showed me the data for how it could remove pollutants, and we became very excited about it. Part of the secret, as I said, was the surface area. We measure surface area in units called meters squared per gram. To try to help wrap your mind around that concept. For this material, they have a surface area of 260 meters squared per gram. That's approximately the area of an NBA basketball court if you could somehow unravel the surfaces of these material and lay them out flat, an amount of material that weighs as much as two $1 bills, so about 2 grams, would cover the surface of a basketball court. But in our hands, it's just this powder that fits into a very, very small glass vial. And so that surface area, as I said, provides access to these cups so that they can do their jobs very quickly. Okay, so this is evidence of that effect. And so we compared our porous cyclodextrin polymer. Fortunately, we were also able to find ways to make a cyclodextrin polymer that has the exact same chemical composition, but a low surface area. So that's shown here in purple. And then we also compared it to a cyclodextrin polymer that had been previously attempted to be commercialized, also non-porous. So this is for the removal of just one pollutant as a model. The pollutant is bisphenol A, so your water bottle stamped BPA free, I'm sure, at this point. And what's notable here is that we can remove a lot of BPA with under the experimental conditions that we chose, but the porous material clearly reaches its maximum binding capacity very, very quickly under these conditions in just seconds. Whereas these other, these non-porous materials, some of those cups are accessible and can bind BPA quickly, but then you kind of slow down and you start approaching their final capacity over a much slower time. And so when you then start looking at that property where you think about packing this material into a column or flowing water through it, that speed is going to be very, very valuable to us. Make this porous material particularly exciting. And so this was even faster than several activated carbons. So this is kind of that same experiment. And again, even though our material has a lower value for its surface area than the activated carbon that we were benchmarking in this experiment, the surface area here works a little bit differently because the activated carbon uses the surface itself to bind pollutants. And so the higher the surface area, the higher the capacity generally of the activated carbon. Here we're using that surface area where as long as it's sufficient to make those cups accessible, we can get this really, really fast binding. All right, another notable thing about cyclodextrin polymers that is not really found for activated carbons or some other adsorbents are that it's actually fairly straightforward to turn this binding interaction off. And that's really valuable to do because at the end of the lifetime of the adsorbent, rather than landfilling it or incinerating it or throwing it away, we can just wash with a different solvent. Here we were washing with methanol, and we're able to wash the pollutants off in a more concentrated waste stream and then reuse the material over and over and over again. So shown here were 5 cycles that we reported in this paper a few years back. And we really see no degradation of the cyclodextrin polymer. Any apparent loss here is just the fact that we're doing a bunch of filtering operations when we were doing this experiment. And so that's really valuable, especially for as we start talking about perfluorinated compounds in a few minutes, because the final solution to those is hopefully to degrade them, just capturing them and removing them and making more contaminated materials is not the most desirable thing. Okay, so building off that one substance that we removed at the time, bisphenol A, we actually, with our collaborator, Damien Helbling, who's an environmental engineer at Cornell, we did, first we dramatically expanded the number of pollutants that we studied. This is a plot of 72 different pollutants, and it's a benchmark of our porous cyclodextrin polymer against activated carbon. And there's an additional aspect thrown into the mix here, and that is that we've included a little bit of a simulant for natural organic matter, so this humic acid, into our water. And so the humic acid is known to foul activated carbon. And so, and that's exactly what you see here. In the absence of humic acid, activated carbon can remove some of these pollutants even more effectively than our materials. But as soon as you start having more realistic amounts of these other natural organic matters, those will stick to the surfaces of activated carbon more strongly than these pollutants will. And so if you look at this plot, it's just removal on both axes. So if you're in kind of the upper left half of the plot, that means the cyclodextrin polymer is removing that pollutant more effectively. And the further off that diagonal you are, the more the differential, the greater the differential between the cyclodextrin polymer and the activated carbon. There's one more thing that was really interesting about this plot. So you see that some of these pollutants are color-coded. Red for pollutants that have a positive charge under the test conditions in water. The gray dots are pollutants that don't have any particular charge, so they're neutral under the test conditions in water. The blue dots are anions in water, and as I'll note later, a lot of the PFAS that we're studying in this talk are anionic, although there are PFAS that fall into all of these categories. And then green are zwitterions, so they contain both a positive and a negative charge. And so you look at kind of the trends here, and one just really jumps out is that you see most of the red dots are concentrated very, very highly up to the top of our removal by the cyclodextrin polymer. And that was really unexpected. And it was a really good thing that we tested this many pollutants and got this strong a pattern, because it gave us a lot of hypotheses. Forced us to rationalize what was going on here, and it forced us to understand our polymer a lot better than we did so far. I'll note that this study was done by Yuhan Ling, who actually presented in Chicago Water Week on behalf of Cyclopure, a company that is commercializing these materials, yesterday. That study with Yuhan was actually done while he was a graduate student at Cornell, prior to him joining Cyclopure. Okay, so the fact that our polymer was binding positively charged pollutants so well, that was a mystery. And the reason that it was a mystery is that we didn't design the polymer to do that. And furthermore, not only was this a new polymer, it was a new type of polymerization itself. So when we reported this material, not only was the material new, the way to make it was new, and it wasn't well understood back in 2016. And so we dove into the chemistry in much greater detail, and certainly with the hypothesis that somehow this polymerization that shouldn't necessarily make a charged polymer, we had the hypothesis that somehow we were getting negative charges into our polymer. And in fact, a graduate student in our group, or former graduate student, Max Clemis, really solved this problem. He went and he looked at this reaction. He studied it very carefully in terms of the polymerization and a lot of other experiments that were complementary. And he found that there was this small side reaction where our Tfn Crosslinker was actually sometimes incorporating an extra oxygen with a negative charge onto that structure during the polymerization. And that side reaction first was one of the reasons that we were getting a fairly low yield in the polymerization in the early days, which we have since solved. But also with the material incorporating some of these negative charges, that all of a sudden was kind of the aha moment where we said, oh, that's why all these cations bind so well to this polymer. So in particular, organic molecules that had a greasy section that interacted well with the cyclodextrin and a positive charge that interacted well with this charge, they were kind of doubly attracted to our polymer. And so that was interesting, and explained our observations that were kind of a mystery at first. And if you want to remove cationic pollutants from water, that is a great material. However, not all pollutants are cations. And in particular, the topic of today for PFAS, a lot of the ones that we care about the most and are at least hopefully on the precipice of being regulated more appropriately are largely anionic. So things like PFOA and PFOS in the news, those were down here, and they're really not removed well by our polymers at all, even though the cyclodextrins themselves would seem to be good binding sites for them. So I haven't said much about PFAS yet, Elena, during the introduction, mentioned them being a very, very important topic right now. Really, we have polluted the entire world with these things. It's a story that is really amazing in its scope and distressing. Is that there are hundreds, even thousands of heavily fluorinated compounds that have been put out into the world, either by accidental release or by incorporating into products, which then that degrade out in our environment and leave behind these perfluorinated compounds. The reason they're left behind is that they are environmentally persistent. They're bioaccumulative in most cases. They are so pervasive that they're in all of our blood, even though we did not intentionally put them there. And they're linked with all sorts of negative health effects, even with low-level chronic exposure. And it's exactly the kind of exposure that many of us are being exposed to. So this is now gaining increased attention. The main places where PFAS contamination exists, generally speaking, are former industrial sites where Teflon or other waterproof products are made, or where a lot of food and beverage containers that are disposable have perfluorinated substances in them as both liquid or both water and grease barriers. And then the other major place where these are found are on military installations, because one of the most prominent uses of PFAS compounds, especially by the military, has been for aqueous film forming foams, which are used to put out fires, especially jet fuel fires. And so this is actually, I think, a slightly outdated map put together by the Environmental Working Group. They release a new map every 4 to 6 months, and each time there are more dots added to it of known sites of contamination. Notably, sampling across the United States is not uniform. So a lot of these places, especially Michigan, North Carolina, and New Jersey, are places where a lot of testing has been done. And as we test more, we find this stuff really all over the place. Okay, so we would like to remove a lot of these perfluorinated substances, and I've introduced already a polymer that is not very good at that. And so this is another way to visualize kind of a profile of how our first polymer worked. And see, it's pretty good for a lot of neutrals. It's excellent for almost any cation you throw at it. And then these anionic PFAS are kind of part of a larger set of anions that are not removed very well. So what we did is that we realized, okay, if we're accidentally incorporating some negative charge into our material, the natural question as chemists is to say, all right, like what happens if we flip that? We actually could be really, really good if we intentionally put positive charges into our material, now perhaps intentionally. And one way that we could do that, one way that Max did that very creatively, in my opinion, is that he took the original polymer and he did one more chemical reaction on it. And so if you look at our Tfn crosslinkers, they've got these carbon triple bonded to nitrogen in the original structure. And Max found a way, he adapted a way to add some hydrogens to those nitrogens, so a process called reduction. And these NH2 groups will actually pick up another hydrogen from water and become positively charged when the material is in water. So that allows us to then look at the effect of what is essentially the same material, but all we did was change the negative charges into positive charges. So great control experiment, but also potentially really, really, really nice for technologically. And indeed, when we did that change, the selectivity of the material reversed almost completely. And so we did the same panel of pollutants in collaboration with Damien Helbling. And now we see most of the cations don't bind well. I have no explanation for this one that still does, but it's certainly an outlier. And then all of a sudden, most anions start to have a very good affinity for the material. And we were delighted to see that among the anions, these anionic PFAS compounds of various sizes were among the most, they were among the strongest binders to this polymer. And so this is kind of another way to look at that complementary selectivity. So now this is that same kind of box plot that I showed before, where the new materials on the left, and if you're above diagonal, this now being a logarithmic, a log-log plot, as you go to this upper left corner, that's dramatically enhanced selectivity for these anions, and all of those yellow dots are the PFAS compounds. So this is a really good visual to show you that not only did we get a material that combined anions well, we got a really good material for anionic PFAS. And then our original one, you can see kind of the cluster of cations plays out visually here in a slightly different way, but you can still see that's pretty consistent. Okay, and so we then started looking more into detail about how well these materials could remove anionic PFAS. And so under comparable conditions, first off, these materials are reasonably fast. It's not seconds, but it's certainly minutes that you can approach their equilibrium binding. Relatively small amounts of adsorbents. And so here, the absolute amount of removal is not the most important thing, because you can actually shift that by using just slightly more or slightly less adsorbent. The speed is really, really good. And what was most notable about this material was not just the results for PFOA, which is here, and PFOS, but this is a whole panel, as I said, of different sizes. And what was even more exciting to us about the profile of these adsorbents is their ability to remove smaller PFAS. So things like PFHXA that's an acronym for a 6-carbon PFAS, as compared to PFOA being an 8-carbon, and PFBA is a 4-carbon PFAS. Those are even more difficult to remove when they have these smaller chains, and many of these smaller PFAS have now been used to replace these larger ones as the larger ones fell out of favor. Which is something I could editorialize about for an entire hour, but will not here. But in any case, the broad spectrum PFAS removal was great to see. The black bars are removal by activated carbon for under comparable conditions, and so this material outperformed activated carbon in several respects. And so we were very pleased about that, and from the perspective of an academic lab figuring out how to design materials to address this challenge, that's what we do within the university. We made these discoveries. We filed patents on these compositions of matter, but along the way, we were interested in seeing, actually developing these materials to be more technologically relevant, and that's again, I think a very important thing to do, and a great interest of mine is to see how much impact these materials can have out in the world. But to do that, my research lab in the Department of Chemistry at Northwestern, we can take these to a certain space, but then we really need more investment, and we need to do things that that are much more appropriate to do within a startup company. And so in 2016, I co-founded a company called Cyclopure, and Cyclopure has had its own research and development efforts ever since. And so I'm not going to go into great detail about what Cyclopure's major efforts have been, although as I mentioned, Yuhan Ling gave a talk just on that yesterday, and so I imagine that will be broadcast soon for those who are interested in it. But generally speaking, the kinds of things that needed to be done over the years as we were figuring out how these materials worked is that they also needed to be scaled up. They needed to be formulated in ways where they could actually be incorporated into specific use cases. And these were all things that Cyclopure has done well over the years. So they actually, in collaboration with Argonne National Lab, developed a first scaled up synthesis of our original material. They also made their own structural modifications. So the material that they call Dexorb Plus is not exactly the material that I described here. It's got its own composition that they will be that is proprietary, but also builds exactly on the design criteria that I've described today. They've also done a lot of work to take a material that's naturally synthesized as a powder and put it into forms where it can be used. So things like papers that have the material incorporated into it, or granules of various sizes that will allow columns with various flow rates, or extruded blocks, such as those that are found in a lot of home water purification systems. And so Cyclopure's launched a couple of products. The initial ones related to PFAS took advantage not only of the affinity of the material for PFAS, but also for the ability to regenerate the material. And so these test kits are essentially the material incorporated into a sampling cup, where a consumer can run some of their tap water through that cup and then send it back to Cyclopure, where they wash the pollutants off of the testing cup and into a mass spectrometer, and they quantify 17 different PFAS compounds and can tell individuals whether they need to worry about that in their water systems. And so this is very, very important, both for in municipalities, if you're interested, but also a lot of people on well water need to test their water for PFAS, and there aren't wonderfully convenient or inexpensive ways to do that. Also for environmental applications to monitor the PFAS at contamination sites in groundwater. There's also these cartridges now commercialized by a company, iFlux, that incorporate some of Cyclopure's materials and work under the same principle as these test kits, just for but for use out in the field. Okay, so where are we going? What's the future here? And so we continue to be interested in these cyclodextrin polymers. And in my lab in the last year or so, has actually gone back and redesigned the cyclodextrin platform. And so I can't disclose these structures in this talk yet, but hopefully in a future water seminar, I'll be able to talk about them. But what we're looking for now is that now that we understand just how important the nature of the linking groups between the cyclodextrins are, they're powerful enough to completely flip the selectivity of the material. We want a way to really be able to dial a composition into the material with essentially complete freedom. And so we've built a new cyclodextrin platform with totally different chemistry in between the cyclodextrins that actually outperforms all of our previous materials and will allow us when you think back to all of those substances at the beginning of the talk, and allow us to target the maximum number of them that are good candidates for cyclodextrin binding, which is quite a few. And then we're also looking at different water matrices as well. And so this is actually an interface between Northwestern and Current and many other organizations. Really, this is a center called CoWork, and it overall is a joint U.S.-Israel investigation for how to purify and reuse water, particularly with a focus for us on wastewater. Israel is a world leader in reclaiming wastewater and using it for agriculture. And to do that safely, we really want to remove a lot of pollutants from that water, such that it doesn't end up in our produce. And so, particularly for PFAS, that is important. And so this is an ongoing effort among many major players here. So many of them listed there. In the last couple minutes, I want to address one more thing, kind of what are we doing right now? And I'll tell you something we are literally doing right now. I'm going to tell you very briefly about a paper that came out, I think 3 or 4 days ago. And related to forever chemicals, I mentioned at some point in this talk, it's not enough to simply remove them, because then you say, okay, then what? And these adsorbents being regenerable is a major opportunity, because we can pack a column and remove PFAS from water and make the water safe, but then we want to wash the PFAS off and be able to ultimately, hopefully, destroy them. And so my academic lab has been studying this problem for about a year now. And our first paper on this topic came out very recently. It's using a technique called ball milling. And so the idea here is that you take your PFAS coming off your adsorbent, and one way to destroy it is actually to apply mechanical energy. You literally agitate it with these steel ball bearings, and put just tons and tons of energy is actually enough to break down these materials at the molecular level. Before we can do that out in the real world, we need to understand this process well. And so there have been a couple reports about ball milling PFAS and showing degradation, but there's very little known about how this works. So this is what postdoc Mohamed Atea, who just recently started at the EPA, has done in our lab. We started looking at ball milling PFOS and found all sorts of interesting findings. First, we ball mill it with potassium hydroxide, which helps to degrade it. Really matters that it's potassium hydroxide. Doesn't work for even other hydroxides. What we're really focused on is studying, okay, how much potassium hydroxide do you need, and what do you get? Right? Because if we just broke down PFOS into other organic fluorines or organofluorine compounds, that probably wouldn't be very desirable. And so we quantified the sulfate. So what's the fate of the sulfur head group off of PFOS, and found that we got pretty much all the sulfate back that we expected. We got most of the fluoride. And now we're looking at this plot over here. We're getting 60 to 80% of the fluoride out, but not quite all of it. And then also we're looking at some of the carbons and what happens to those. And at first we found formate, which was interesting, but only one molecule of formate for PFOS. So that accounts for one of the 8 carbons, but not the other 7. Ultimately, by looking at this reaction very, very closely, Moha discovered, first off, that ball milling looks pretty good. We can completely destroy PFOS. We get 1 molecule of formate out. That's pretty benign. The rest of the carbons seem to come off as carbonate, which is also a benign ion. Right? Sodium carbonate is just baking soda. So it's essentially turning this stuff into CO2. The extra fluorine that we can't account for is still bound to carbon. It's bound to carbon as some sort of polymeric CF containing material that we don't understand yet. So it's unlikely to pollute water. It's completely insoluble, but we're still figuring out where, exactly what that is. But overall, we're very excited about this and in fact, other emerging PFAS destruction technologies. I'll stop there. I have to thank our excellent collaborators over at Cornell, led by Damien Helbling, and then a wonderful team of graduate students and postdocs who have contributed to this work over the years. Dr. Aladdin Alzbaiyi now works for DuPont. He made the initial discovery of these cyclodextrin polymers. Max Clemis discovered this charging effect. Lei Zhao, a former grad student in our group, was a major player in PFAS removal as well. Mohammed Ataya, I mentioned, has contributed to a lot of these projects, including the ball milling that was recently published. And we have a early stage grad student, Jiwei Lin, who's working on these new adsorbents that I mentioned only in the future work. This has been funded at various points by the National Science Foundation, by the CERTIT program, which is a joint effort of the DoD, EPA, and DOE, the Camille and Henry Dreyfus Foundation, and then most recently by the Byrd Foundation with our center with Israel. Thank you very much for attending this webinar, and I'll be happy to answer questions.
Thanks so much, Will. We have a big queue of questions. I'm going to start you off with a really easy one. What's the meaning of the Hummingbird and the Dichtel Research Group logo?
Oh, no. So, yeah, the short version of the story is that I had an overzealous web designer when I first started my group at Cornell, and he said that I needed a mascot. And so I jokingly said, okay, well, I really like hummingbirds. So not thinking that would ever last beyond more than a couple weeks. But then soon we had students in our group dressing up as hummingbirds for Halloween, and we have it on our lab coats and all of our merch. So it's here to stay.
Okay, well, we have lots of fans of the logo, and yeah. Now I want to get into there's a range of tougher questions, or more technical questions that are concerning the binding mechanism and the matching between the cup size and the target. So a question about how beta CD can be so effective at basically adsorbing targets of very significantly different sizes if it's all dependent on this like close matching. So can you dig into the matchmaking there and how that works, that function works? And I've got some follow-ups on that. Yeah. Yes,
cyclodextrin, it's an amazing molecule in this way. And so it's small enough to be selective for compounds that happen to be of the size of the things that we care about separating. But within that range of it not grabbing gigantic molecules, it's actually a pretty promiscuous binder. So it can bind small molecules and have a really nice fit, like PFOA fits in there just about perfectly. But if a larger molecule just has a piece that can fit into it that is of the right chemical composition, it's got space on both ends of the cup where other parts of the molecule can still kind of stick out a little bit and interact with perhaps if the polar part of PFOA can stick outside of the cup and either interact with the OH groups on the sugars or even water outside of the cups. So even the fact that instead of being kind of cylindrical, these are really like the walls are kind of slanted. That also kind of is much more tolerant of molecules of different sizes. So like cyclodextrin was just kind of naturally had all of those characteristics that let it be so magical.
Yeah. So, and then I guess the reverse of that, but if it's binding, if functionalized cyclodextrin is binding anions very broadly, how do you keep it from being saturated by other anionic interference before it gets to the PFAS?
Yeah, I think that we see that as we've studied dirtier water matrices, you definitely can see effects of fouling in that, you need to use a little bit more material. The dirtier the water, the more adsorbent you have to use. But by and large, what we found is that activated carbon tends to get fouled to a much greater degree and by more things than these cyclodextrin polymers. So it would never be realistic to say, okay, these are going to behave exactly the same in absolutely pure, nanopure lab water as compared to other, more realistic water matrices. But generally speaking, these cyclodextrin polymers are pretty forgiving for fouling, and also water does not tend to have a ton of organic anions that often compete for PFAS so much, right? Like inorganic anions are not going to be competitors. It's really only organic anions that you have to worry about.
That's great. And then have you tested it, how it would behave in other organic bulk like oil, or is it mostly in water? This is only in water.
Yeah, this is in water. There are other fluids that are of interest, but it's really in water where it's that interior pocket being greasy gives you a contrast with water. But then when you start looking at other, like if you're to start putting this in oil, like the bulk oil wouldn't be, quite as different as compared to the interior of the cyclodextrin as the contrast between bulk water and the interior of the cyclodextrin. So the other solvents are actually ways to regenerate the cyclodextrin polymers.
Got it. Are there any databases available that can share the binding affinity between beta cyclodextrin and various different PFAS, or does that not exist yet?
There's not one resource for it, because cyclodextrin has been studied really for 30 years in various contexts for actually longer than that. One thing that's notable, actually, Damien Helbling's group actually ultimately tested enough pollutants where they could develop a predictive model for unknown pollutants based on the molecular characteristics of the binding of 200 pollutants. And so for any given cyclodextrin polymer, like, you wouldn't do this for every single one we make in the lab, but for one that is commercially relevant, that can be profiled to a degree where we can have a very high degree of confidence for figuring out whether it will bind even things that haven't been tested yet.
There's a question about the pH. Is there pH a dependency here for the anion CDP, or does it have to have like mild acidic conditions to specifically protonate that way? Yeah. So what pH can do is that it can change the charge state of the pollutant itself, or it, in certain adsorbents, it could change the charge state of the adsorbent. Generally speaking, like we're designing adsorbents, especially now that we know exactly what we're doing with the combination of charge and cyclodextrin, where the adsorbent itself will be pretty pH invariant. Generally speaking, PFAS are easier to bind under more acidic conditions, but that in some contexts that's kind of cheating, right? Because you can't necessarily change the pH of your water only to remove them. So but there are dependencies, but generally, we're focusing on really the performance under kind of the pH 7 or thereabouts, right? Because that's going to be the most relevant for most use cases. Right. I want to close on a couple of use questions. We are right at time though, and we've got a poll up on screen for you to participate in. While we're doing that, I will leave the chat open and we'll keep going because there's a ton of questions. So as long as we can, but there are questions about, with all of the knowledge that you have, do you drink tap water in the US? And even if you do, are there water filters that you recommend? You talked a bit about the consumer product side of this. Like, what advice can you give to folks that are, have concerns about this showing up in drinking water?
Yeah, well, so I tested my water at home and was pleased to find that here in the North Shore, we're pretty free and clear of PFAS. But Lake Michigan
drinking water is your source.
Yeah. So I, but this is a really I mean, that's kind of a flip answer, right? Because there are a lot of people in the United States whose water is contaminated. And I don't think there is, there's not a great solution out there now. There are some home filtration solutions in places where this contamination is recognized, and particularly where it can be blamed on someone able to pay for it.
Yeah.
There are some communities where people are being provided home solutions that are then maintained. But I mean, that's really not a solution for a lot of people. It's really economically out of reach. So I generally drink tap water, and I'm sure I've never had my blood tested for PFAS, but I'm sure it's there.
Yeah. And then I guess, final question. So how far in the future do you think this sort of technology is widely adopted, both in the drinking water utilities, and then specifically there was a question about in our water and sort of wastewater plants? Like, there's a long way to go to sort of full-scale utility adoption, but what's your forecast, and maybe what's the role of regulation in helping to speed that along?
Oh yeah, it's a long time before this is going to be done at the municipal level. I think, and rightfully so. Municipal water purification is a pretty conservative place to incorporate new technologies. You have to be certain that something is economically feasible. You also have to be certain that technology is going to be around if you're going to make a capital investment into doing it. So, I think the pathway for these technologies is in, more distributed uses first, and, proving their value there. The drinking water side, the wastewater side, is also going to be the most price sensitive market out there, right? And so, that's it'll take time. I mean, I think we're talking decade or more. But you mentioned regulation, and in the U.S. we are absolutely dropping the ball in this regard, and the entire structure of how we regulate organic contaminants is broken. No more so than in PFAS, where companies have known that these compounds are toxic for decades. They hid that information. They used drop-in replacements as they phased out PFOA and PFOS that are equally bad, almost certainly, and continued to make irresponsible decisions with the health of everyone on this planet.
Yeah.
And so we have not regulated that appropriately. We absolutely need to regulate PFAS as a class, so that we're not just playing whack-a-mole with just PFOA or just PFOS, right?
Right. Well, thank you. I mean, I appreciate the sharp point on that. I think it's critical that we have that call to action and widespread recognition that we're just not going to get there fast enough without the regulation to support it. I'm going to stop the recorded talk here and say thank you to you, Will, and to all of your collaborators. I mean, obviously this screen is just, shows how much collaboration from so many different levels of institutions and funding sources it takes to bring something like this into the market. Really appreciate your work. On behalf of all the collaborators, thanks to everybody for joining us today. And we will keep the chat open, because I think there are some questions, if you have a bit more time, that you might want to answer there. But thanks so much, everyone, for joining us, and look forward to seeing you around at other Chicago Water Week events later this week.